In this video, we're going to define something called a prime ideal, and then we're going to look at a couple of examples. So let's start with the definition. Let's let R be a ring, and I want P to be an ideal of R. And we are going to call P a prime ideal of R if P has the following properties. And the first property is that P is going to be a proper ideal. In other words, P is a proper subset of R. So P is included in R, and P is not all of R. The second property is stated as an implication, and it's really where the language prime ideal is going to come from. If A and B are any elements of the ring R, and their product, AB, belongs to the ideal P, then we're going to be able to conclude that either A belongs to P or that B belongs to P. And like I said, it's this particular property that's going to give rise to why we want to call them a prime ideal. So I want to look at some examples. Our first example is going to be the prime ideals of the integer ring. So in other words, what are the prime ideals of Z under its usual plus and times? Now I do want to recall that I already know that every ideal of Z is a principal ideal. And in fact, if I is an ideal inside Z, so this is an ideal of Z, then we can actually write I is either going to be the ideal generated by 0, or I is going to be the ideal generated by N, where N is the smallest positive element of our ideal I. And I want to look at the two cases separately. So the first case, let's think about I being the 0 ideal. And the question is this ideal a prime ideal? Well, let's see. Is this guy a prime ideal? Well, let's think about this. I know that the ideal generated by 0 consists of just the 0 element. So if I know that AB belongs to this particular ideal, then I do know that A times B is equal to 0. And since we are in the ring of integers, AB is equal to 0 does imply that A is equal to 0 or B is equal to 0. And so that does say that either A belongs to my ideal or B belongs to my ideal. In other words, yes, this ideal is a prime ideal of the integers under their usual multiplication. So now let's look at the second kind of ideals. We're going to let I be the ideal generated by N, where I know that N is a natural number. Now the first thing I want to note is this. If N is equal to 1, then the ideal generated by 1 is actually all of the set of integers. And so the principal ideal generated by 1 is not a proper ideal, so it is not a prime ideal. So now what I want to do is I want to assume that n is bigger than or equal to 2. And when is the principal ideal generated by that particular n a prime ideal? Well, let's just consider that question. I know that this particular ideal is equal to all of the multiples of n. Let me actually write them as q times n, where q is any integer. And I know what a prime ideal is. This ideal is a prime ideal, will be true if and only if we have AB inside the ideal implies either A is inside the ideal or B is inside the ideal. Now, this logical statement can be translated into other language. Keep in mind that the ideal generated by n is nothing more than the set of multiples of the integer n. In other words, you get into the principal ideal generated by n by being divisible by n. So we can take this statement here, and it will be true if and only if n divides AB implies n divides A, or n divides B. And this particular statement starts to look a lot like some facts from number theory. Facts that we've actually known since about middle school. And I want to kind of box this in as a recall from number theory. We know that if P is a prime number, then we have P divides AB will imply that P divides A or P divides B. We also know from number theory that if the number n is a composite number, then we know that P divides the product AB does not imply that P divides, oops, I should be saying n's here, so let me get my notation consistent. So if n is a composite number, then n divides the product AB does not imply that n divides A or n divides B. And the reason why is that the prime factors of n can be split up between both A and B. But the net result of both of these things is that we have as a very important factor, and I'm going to write it over here, that you put these two things together and you get, in the world of integers, we have, if a number divides a product, implies that thing divides one of the two factors in the product. That statement is true if and only if our number is indeed a prime number. And, well, or n is equal to 1. But we've already said that n is not going to be equal to 1. So what this means is that from number theory, we can put this back and we realize that n is a prime ideal happens if and only if n is a prime number when we are knowing that n is bigger than 1. So this guy is a prime ideal, and n is bigger than 1 happens if and only if it is a prime number. And it's this connection why we want to call these ideals prime ideals. They behave the same way the prime ideals p times z behave. So that's where the language comes from. And that's enough for this particular video.